Hey guys, welcome to your Unit 9 Lesson 7 notes on exponential functions. Today we're going to put the fun in function. Haha, okay, anyway. By the end of the day, you will be able to graph exponential functions. And the good news is you can always make an You can always make an XY table when in doubt. But I'm going to show you some shortcuts. To give you a real-life example of what an exponential function is, go ahead and find a piece of paper and fold it in half. After you unfold it, so you've got your piece of paper, okay, you fold it in half. Now you have two sections. 1, 2. Now fold it in half again. This is your second fold, and now you have 1, 2, 3, 4 sections. So after 2 folds, you have 4 sections. Okay? Now fold it in half again. And when you unfold it, you'll notice that you have actually 8 sections after the third fold. Keep doing that process, keep folding it, and see how many sections are formed by your creases, and see how many sections you can get. After your fourth fold, you have 16 sections, and then you'll have 32 after the fifth fold. And after that, the paper gets kind of thick and hard to fold, but if you manage to do it, there would be 64 folds. And then even then, there'd be 128 folds. And I think it's been like impossible to fold back then. Anyway, what's the pattern? Well, the first time you folded, it's just 2. There's no pattern yet. But then you have 2 times 2. And then you have 2 times 2 times 2. Because each time, you know what? I wrote that wrong. I'm going to start over. You have 2. And then you take what you have, and you multiply that times 2. And then you took what you have, and you multiplied times 2 again. And then you took that, and you multiplied times 2 again. Okay. So this is 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power. You'll keep going to the fifth power, 2 to the sixth power, and 2 to the seventh power. Oh, and check it out. Each time our exponent goes up, that matches exactly what our x is. This is an exponential function. So although our result is, they're powers of 2. So exponential functions, just like this is the function of, if this is our x and this is our y, the pattern here is that y equals 2 to the xth power. That's what all exponential functions are going to look like. They're always going to be y is something to the xth power. So you always have y equals some number, whatever that number is, any number, get an A for any number, raised to the xth power. And that x as an exponent is what makes it an exponential function. Y equals a to the xth power, and then sometimes you might have a little like plus c on it for just a little extra oomph there. Okay. Now let's, we didn't even graph it. Make a graph of your findings. Sorry, forgot to graph it. Okay. So at our first fold, or when we had 0 folds, we actually had 1 section. After 1 fold, we had 2 sections. After 2 folds, we had 4. At 3, we had 8. At 4, we had 16. After 5 folds, we had 32 sections. After 6 folds, we had 64 sections. Let's say about halfway is like there. 64 sections. And then after 7 folds, we had 128, which is off our graph. So our graph, I had a student once who would like connect each dot like between them like this just to help her give her the shape. And that's a good starting point. That's not what your graph is going to look like, but it does help if you're looking for the overall. There's like, it should be curvy guy and then way up high like that. That's what all exponential growth will look like. Now the initial value is this guy right here. Initial is your starting, like my initials are AV, because that's what my name starts with. So the initial value is your starting point. It's the value that you have when x is equal to 0. And it will always be A. It will always be this number right here. If there's no C. If you don't have this guy in the picture, then it's just that A value. It's also always going to be considered the y-intercept. So when x is 0, that's your initial value right here. That's your starting point. Just like we started we didn't start with 2 sections. We started with one paper, one section. So that's exciting. This graph will not go past the y-axis. It will always go, it will get increasingly close to, if we had gone backwards, it would go like a half, a quarter, stuff. It will get increasingly close to that. And we call that an asymptote, and I need purple. So we would say, actually, I want this to be this guy. Okay, sweet. We put a little dotted line for this guy. It's going to be right at y equals 0. But that's your asymptote. It does not cross. It doesn't touch that line. Asymptote. With a P. So that's fun. Okay, cool. Honestly, guys, your asymptote will always be at y equals 0, unless there's a plus c, then it'll be at the c. So I just plug in x's and y's. I call it good. So start with some little negatives. 0, 1, 2, 3. That's honest, guys. Go with those. Go with those all the time. So I'm going to put those in our charts real quick. Go with easy numbers. Go with small numbers. Okay, so now we need to take our rule. What is 5? Oh, just kidding. What is 5 to the xth power? Looking at this, is this exponential? Yes, because it's y equals some number to the xth power. You already know that your starting value is going to be 5. We're going to call it, oh, I'm just kidding, initial. We're using proper terms now. I'm going to call it right now. That's our initial value. That's what happens when when x equals 0. So I'm going to call that's... oh, wait, no, it's not. Just kidding. I lied. Forget I said that. It's not A. I didn't do that. That was wrong. Okay, anyway. So now let's plug it in. We've got 5 to the negative half power. I want to scoot this over. 5 to the negative first power, 5 to the 0th power, 5 to the first power, 5 to the second, 5 to the third. This sounds like a weird rap. It's not. So we took all of our values for x, and we plugged them in for x, and now we need to figure out, how are we going to simplify this? Let's start at the bottom this time, because that's going to be easier. 5 to the third power is 5 times 5 times 5, which is 125. That's major. Okay, 5 squared is 5 times 5, which is 25. Honestly, guys, if you can make the leap from 5 squared to 25, you don't need to show these steps. Same thing, if you just remember that 5 to the first power is just 5, great. If you remember that 5 to the 0th power is just 1, awesome. Go for it. Now there's 2 ways to fill out this table. I'm going to show you the technically math way, and then I'll show you the shortcut way. So you look at this and you go, oh, negative exponent. That negative becomes a fraction bar. So that's the same thing as 1 over 5 to the first power, which is 1/5. Cool. Same thing here. You remember that negative exponent becomes a fraction bar? And you say, oh yeah, awesome. That's 1 over 5 squared, which is 1 over 25. Cool. But let's say you forgot that rule temporarily. Like you know it, I know you know it. But you forgot temporarily and you didn't know what comes next. You can always look at the pattern that you've already formed. You could say, okay, well, to get from 20 here, this is just divide by 5. Okay, cool. And then to get to our next step, that's just divide by 5. Okay, cool. And then divide by 5. Okay, cool. And then divide by 5. Oh, 1 divided by 5 is just 5. Oh, yeah. Okay, right, cool. So if you forgot, you can just always keep that pattern going. That's fine too. Hey, we've got our x's, we've got our y's. Let's plot them. So go -2 up 1/25. Who came up with this? Ugh, it's just tiny right there. Same thing, 1/5. Okay, cool. And then 1. Sweet. All right, okay. Now we're in business. Over 1 up 5. Over 2 up 25. Over 3 up, yeah, that's not going to happen. Remember, we need to have an asymptote right here at y equals 0. That's a straight line, by the way. Oh, okay, don't tell my mom, she's an art teacher, and she would be embarrassed at my lack of art skills. She actually wouldn't. She would probably be proud of me for just trying. I could call her up right now and see, but yeah. Oh, boy. There it goes. Oh, little arrow hat. There, that's exponential. That's a steep one. Okay, this same thing, you're just going to plug him in. You can take your little xy guy, make him your exponent, put the x in exponent, and call it a day. Okay, so we've got 3 to the xth power. 3 raised to the power of x. So that'll give us 3 to the -2nd, 3 to the -1st, 3 to the 0th, 3 to the 1st, 3 squared, 3 cubed. Again, guys, I like to start at the bottom because I think that's just easiest. 3 cubed is 3 times 3 times 3, which is 27. That's not centered in the box, and that's by me. 27. 3 squared is 3 times 3. We're going to do this fast. Okay, 9. 3. 1. 1/3. 1/9. Also notice the relationship here. 3 squared, 9, 1/9. Oh, that's no coincidence. You can use that to your advantage. And now we just put up on our graph. Okay. -2, 1/9. Still tiny little fraction guy. Tiny little fraction guy. 1. 3 is like here-ish. 9 is like there-ish. I think a little higher actually. Meh. Good enough. And 3 is 20. Oh. Like there probably. Don't mind my voice. Whoop. Oh, we forgot to draw our asymptote in. Look, an asymptote appeared magically, mathemagically. Ta-da! Don't cross that line. Get infinitely, tinily close to it. Never touch it. No touchy. Okay. Sweet. Now I got one more. Ooh, fractions. Don't let them scare you. I like fractions, actually. So we need to figure out what is 1/3 raised to the x power. And that's an x. And here's where it gets fun. Because we actually need to think backwards. Okay? Okay. So we have 1/3 to the -2nd, 1/3 to the -1st, 1/3 to the 0th, 1/3. Man, I love the power of 1. You guys, it's just always that thing. Isn't that so great? Okay, anyway. Also, to the 0th power is just 1. Isn't that so great? 1/3 cubed. No, I'm serious, guys. You should always start with your big X if it's worth exponents and then work down. It's just so much easier. So when we have an exponent on a fraction, we can distribute him. This is the same thing as 1 cubed over 3 cubed. 1 cubed is 1, and 3 cubed is 27. I feel like we just did this. What a coincidence. Okay, same thing with this 2. We can distribute him, which gives us a 1 squared over 3 squared. 1 squared is 1. I love 1. So good. 3 squared is 9. I feel like I've seen this pattern before. Crazy. Right? If you notice, we are multiplying by 3 every time. That's our pattern. If you want to keep doing this pattern, up, 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 it will work. I promise. These come out to be 3 and 9. And notice, it's not -3. It's not -9. Even though these are negatives, we still get a positive number. This is because the negative actually flips our fraction upside down. This is the same thing as 1 over 1/3 squared, which fancy fraction rules gives you 3 squared. This is the same thing as 3 to the first power. Which, oh hey, look, we found already. Oh man, where did my axes go? I didn't put axes on these. We'll draw our own. So that means x needs to go from -2 to 3. I'll just put him in the middle. So 1, 2, 3, 4. 1, 2, 3, 4. We need to go up to 10 because our biggest y is 9, but 10 is just such a nice number. I'm going to go try every other one, see if that works. 1, 2, 3, 4, 5, 6, 7, 8. Well, we made it to 9. That's what we're gonna do. Okay, cool. So we go back -2, up 9, over -2, up 9. That's where the point is. Okay, look at me using like rulers, old school. Over 1, up 3. Okay, I don't need this anymore. Then over 0, up 1. Over 1, up 1/3, a 9th, a 27th, baby little point there. We still need an asymptote at 0. Sweetums. Let's just draw our graph. Okay, good enough. Cool. Now remember initial value. The initial value was always what happens, what is y, when x equals 0. What is the same about all the initial values? When x equals 0, y is 1. Super duper, right? Okay. The only way to change that is by adding or subtracting. Okay. Did we do 2 to the x yet? No. But we did 3 to the x already. Nice. Okay. Look, guys, I'm going to take our 3 to the x answers. I'm going to duplicate them down here real quick to save us some time, because this is a video and not a live lesson. Okay, cool. So what happens if we have 2 to the x and then we add 3? Well, we're still going to take our x and we're going to plug in an x for our exponent. And then we're just going to add 3 to it. So we get 2 to the -1/2 plus 3. Don't mind me. Just trying to do this fast. Yoink. Nailed it. Okay, 2 to the -1/2 plus 3, not half, to the -2 plus 3, to the negative first, do. Ah, okay. 2 to the -1/2 power is the same thing as 1 over 2 squared plus 3, which gives us 1/4 plus 3, which is 3 1/4. If you need more help with that, let's go over it in class. 2 to the -1/2 is 1 over 2, so that's 3 1/2. 2 to the 0th is just 1. 1 plus 3 is 4. 2 plus 3 is 5. 4 plus 3 is 7. 8 plus 3 is 11. And fun fact, if we had done 4, we would have gotten 19. So that's exciting. Okay, now let's graph it. But where's our asymptote this time? Our asymptote is at y equals 3. Asymptote, where did you go? Shooties. Oh, here he goes. 1, 2, 3. Ta-da! Okay. Back to up 3.25. Yeek. 3.5. Yep. 4. Nice. Over 1 up 5. Over 2 up 7 is like there-ish. 11 is like there-ish. Oh, 19 is like up here. Cool. Hey, we've got our points. Connect them. So what's our initial value? It's at 4. So when I'm looking at graphs, this is what I look for. I look for 3 things. I look for your shape. Is your overall shape the same? That is, you didn't draw me a line. You didn't make me a parabola. You didn't give me like a circle or like a square root kind of deal. No, it looks exponential. Okay, cool. I also look at your asymptote. Is your asymptote in the right place? Like literally draw it in. I'll also look at your initial value. That's this blue spot when x equals 0. So that's fun. All right, one last one. Oh, asymptote. Let's put our asymptote on here. Asymptote here is going to be at -1. Bonk. Close enough. Okay. So we got 3 to the x. We need to add a -1 to each of these guys. Oops. Okay. Remember from last time, did I put these in here? 3 to the x. Nice. Here's our 3 to the x. We just need to subtract 1 from each of these guys and call it good. So 1/9 minus 1 is 8/9. That's 8/9. I'll just rewrite that one. 1/3 minus 1 is -2/3. 1 minus 1, that's fun, that's 0. 3 minus 1 is 2. 9 minus 1 is 8. And 27 minus 1, 26. And fun fact, 4 would have come out to 80. But we're going to get off. We're going to get off before that. Okay, now let's put them on our graph. We've got our x values. So we got -2, 8/9 is almost 1. I'm sorry, this is -8/9. Okay, -2/3 is almost -1, but not as negative. 0 is just plain 0. Cute. Over 1 up 2 is here-ish. Cool. Over 2 up 8. Might be a little too high. Close enough. Over 3 up 26. Yowza. That's way up there. And yeah, that we're not getting to that 4. Okay, sweet. Is our initial correct? 0, oops, that's not a highlighter. 0, 0, looks good to me. Got that initial. We got our asymptote here. Need to make sure do not touch it. We get so infinitely close to it, but never touch. It's like the saddest love story in all of mathematics. We grow ever so closer together, but never actually touch. Aww, but not. Cool. Hey, we got our shape. We got our initial value. Awesome. Got our asymptote. So what do you notice about the initial value to these functions? Well, it should be at 1, but then you subtract or add the constant to it. So it's the asymptote. So they cause us to move the asymptote down, but the initial value is always 1 above where the asymptote is. So it's always the asymptote plus 1. Cute, right? Cool. But how are we going to use this in real life? Well, I've been using exponential functions lately. We're talking about loans and taking out house loans and stuff. So let's say that Mariah's parents or an adult in Mariah's life loved her And they literally invested in her. So when she was young, she had a certificate of deposit for a bank account. So someone put $2,000 into a bank account that had an annual interest rate of 6%. Pause. Whenever you have 6%, actually, I want to use this. Money. Don't think of it as 6. Think of it as 0.06. And here's my other hint. It's an interest rate. You're gaining stuff. So you're taking 100% of what you're earning plus your 6% is going to give you 1.06. Whoa. Okay. So after 8 years, how much money will she have in the account? So we start out with $2,000. That's the initial amount. Fun fact, in money terms, we call this the principal. Not like the principal of the thing, that's PLE. But principal is the amount you start with. Ooh, fancy. Okay, anyway. So after 0 years, right when she started, she had $2,000. Cool. But then, the next year, she had $2,000 times 1.06 of $2,000. And then, I'm going to put this in parentheses, just because I like that better. And then she had that same amount, but whatever that was, they also multiplied that times 1.06. And then, the next year, she had $2,000 times 1.06 times 1.06 times 1.06. Guys, that took up so much space in their calculations, they had to actually shrink it down like that. I'm just kidding. And so on and so forth. I'm not going to write all the steps because I think you're starting to see the pattern. Oh, I didn't write the year. No, that's not the year. That's the amount. So that's the total. Sorry. Was 20,000. Next year, she had 2120. The year after that, she had a long number because it's got a decimal. I'm going to round it up to 2247. And then the next year, she had 2382. Okay. So what is the pattern here? Every single time, we're multiplying times 1.06. That is, we're taking whatever we have, and it's 2,000 raised, or times 1.06, that many times. So if the year is X, the amount we get, actually, let's do T for time. I know X for exponent is fun because it sounds like exponent, but let's do T for time. So that's our rule. It's 2,000 times 1.06 to the power of time. Ah. Cool. So now we can deconstruct this. How much time was spent? Oh, shoot. This was after 0 time. So we didn't multiply times 1.06. It was just times 1. Then after 1 year, 2, 3, 8. So after 8 years, what is she going to have? Turns out this is 3188. Approximately. We should have gone into cents, but then that wouldn't fit in my box. Cool, great? Cool, great. Hey, look, this pattern, that's basically what we're going to use. Except, what was 20,000? 20,000 was our principal. Ha ha ha. I'm going to use that. So if you deposit, first spell it right, principal, that's the amount of money that you put in, P, into your account at a rate of R, so it's actually 1 plus whatever your rate is. Just remember to express it as a decimal in here. I'm sorry, we call it an annual interest rate. It's like and rate, doesn't make sense. Like this. Then the amount in your account, amount A. So amount, I'm sorry, A can stand for amount or it can stand for account, whatever you want. And then here 8 was our time, how much time had passed in years. Oh, hey, look, there it is. So R is your rate, P is your principal, T is your time. Isn't it pretty? Get it? Pretty? Okay. Well, let's say when Luke graduates high school, he's going to deposit $2,000 in an account with an annual interest rate of 3%. After 4 years, let's say he goes to college or something for 4 years, how much money will he have in his account? Just by doing anything. He's just going to leave it there, leave it alone. Okay, let's use our formula. What is our principal? How much does he start with? He starts with $2,000. Oh, that's boring. That's what Mariah did. I should use a different number. Too late. Interest rate of 3%. It's not 1 plus 3. Holy cow, that would be way fast. No, it's 1 plus 3% as a decimal. 0.03. Now I wrote 0.03 because then we can just do 1 plus 0.03 is 1.03. Oh, cool. It's like up here when we had 1.06. Ah, 1.03. Okay, 4 years. Bonk, bonk. If you want to do that by hand, you knock yourself out. Plug it into a calculator. But remember your PEMDAS, you need to do this first. Tell me what your final answer is, and have a wonderful time in your homework. Let's go back to your graphs. Remember to get the shape like this or like this. The asymptote and the initial value is at x equals 0. Have a wonderful time in your homework.